Hi folks, I made this video to go through 3 different examples of using the right-hand rule to predict force directions of charged particles moving through magnetic fields. And one thing I'd like to review really quickly is the magnetic field itself and what it means. Number 1, this is how the magnetic force is calculated on a charged particle, F equals QVB. And keep in mind that the V has to make a right angle to B. We'll see where that's relevant here in the next video. 2, therefore the magnetic field strength is defined as force per unit charge velocity and has units of Newton over coulometer per second. 3, I'd like to review the direction of the magnetic field and how it's defined. And the direction of the magnetic field doesn't have a very scientific type of direction to it. It's defined as the direction that a compass points. So let me put that up here. Direction that a compass points. Okay? So, I'm going to go through these 3 examples. Here is a picture of a charged particle, positively charged, velocity vector points up. There's a magnetic field, or I sometimes refer to them as a B field, pointing to the right in this direction. And what that means is, whatever point in space this is, if I put a compass here, it's going to point in that direction. Okay. To get the direction of the magnetic force, we use what's referred to as the right-hand rule. You take your fingers and you put them parallel to the velocity. Then you rotate till you can sweep towards the magnetic field vector. Now the magnetic field points this way. In order for me to sweep towards the magnetic field, I have to rotate my hand like this. See how I'm now sweeping towards the magnetic field. My thumb tells me the direction of the magnetic force. So that magnetic force is into the board, or in a mathematical sense, we would say that's in the negative z direction. Now, it's also tough to draw vectors in 3D. So there's kind of a notation that goes along with this. When vectors are pointing towards you, we typically draw them like that. And when they're going away from you, we usually draw them like that, with the arrowhead going away. So I can draw the force vector on this. I'll just draw like a circle with a line or a cross through it. And this represents a vector going away from us in the minus z direction. So again, that's coming from V, sweep towards V. Okay. Another example. Here, the magnetic field is away from us. That's what that symbol means. Meaning that if I put a compass here, the needle will want to rotate around it and point that way. The velocity of the charged particle is to the right. So to predict the magnetic force direction on it, we take our fingers, put them in the direction of the velocity, which would be this way. You have to do this very methodically. You can't just kind of softly, about this way. You have to make them nice and straight, put them right parallel with the velocity. Now, the magnetic field points this way in the minus z direction. So you need to rotate your hand so that you can sweep towards the magnetic field. That's what I call sweeping. Or another way to think about it, your palm should point towards the magnetic field. Thumb tells you the direction of the magnetic force. So the force direction on this particle is straight up. Meaning that this particle will deflect up. Okay, this example, 3rd one. The magnetic field is at you. That's what this vector represents. The velocity is down. So what I'd like you to do right now is hit pause, apply the right-hand rule to this, and predict the force direction. Okay, do that. Okay, hopefully you've checked that out, and let's see what we get for an answer. So in order to predict the force direction, you should have taken your fingers, put them in the direction of V. Now, you need to rotate your hand until you can sweep towards the magnetic field. Now, the magnetic field is coming right out of the page, basically. So I would need to rotate, sweep towards B, or think of it as your palm should point towards the magnetic field. Thumb tells you the direction of the magnetic force. So hopefully you got that correct. Left is the correct result. This is how we calculate magnetic force on positively charged particles. I'm going to go through one more example with a negatively charged particle. So let's say, for the sake of example, the magnetic field points up. And we fire an electron, or a negatively charged particle, into the board this way. So the velocity vector I would represent like this, v. So that particle's velocity is this way. There are two ways we can actually calculate the force direction, or predict the force direction on this particle. The first way is to use the standard right-hand rule, like we always apply it, and then just reverse the direction for the fact that the thing is negatively charged. If we do so, put our fingers in the direction of v, rotate till we can sweep towards B. Thumb tells us the direction of the magnetic force if it's positively charged. This thing is negatively charged, so the force direction is left. Now, the other thing you can do, I've never actually seen this in a textbook anywhere, but it does work every time. For negatively charged particles, you can use your left hand. Fingers in the direction of V. Rotate till you can sweep towards B. Thumb will give you the direction of the magnetic force on a negatively charged particle.